Okay, we are on to question number 25. And for the first part, it's given the function is y is equal to under root ax plus b, and we have to prove that y into second order derivative plus square of the first order derivative is equal to 0. So let's write down our function first. The function is y is equal to under root ax plus b. Okay, so this is our function, and to eliminate root, we can square on both sides. So square on both sides gives us square of y is y square, and the square of right hand side is, this is equal to, now y square is equal to ax plus b. Okay, let's differentiate this with respect to x. So differentiating with respect to x, we get, okay, now differentiation of y square is 2y, and y is dy by dx, and differentiation of ax plus b, b is a constant, a and b are constant, so a is out and differentiation of x is 1. And yes, we have to get the second order derivative, so let's differentiate it once again. Let's take 2 common, and this is u into v, so it's v into differentiation of y, which is again dy by dx plus dy by dx into differentiation of y, sorry, y. So this is second function into differentiation of first plus first into differentiation of second function, which is dx square by dx square. So this is the second order derivative, and the differentiation of constant is 1. Okay, now, so okay, the differentiation of constant, sorry, is 0. So this is 0. Now 2 when shifted to this side is also 0. So finally we have, we can write it as, this is y into the second order derivative plus, and this is the square of the first order derivative, which is equal to 0. And that's what we have to prove. So we are done with the part A. Now let's move on to part 2. So for the second part, it's given that the function is differentiable in open interval 0 to 2. And let's write down the function first. So the function f of x is equal to, this is ax plus b upon, sorry, ax plus b. So the function is ax plus b when x is greater than 0 but less than equal to 1. And this is 2x square minus x when x is greater than 1 but less than 2. Okay, now the function is differentiable in 0 to 2. So that means it's also continuous in 0 to 2. So given function is differentiable in 0 to 2. So that means function is also differentiable at x is equal to 1. And as the function is differentiable in 0 to 2, so that means the function is continuous on 0 to 2. So that means that the function is continuous. 0 to 2 means function is continuous at x is equal to 1. So let's try to use these two conditions. So when the function is differentiable at x is equal to 1, that means this will give us that left hand derivative is equal to right hand derivative at x is equal to 1. So let's find out the left hand derivative. So left hand derivative is limit x. So we will evaluate it for the limit h, and its left hand derivative. So this is f of x plus h minus f of x upon h. And the right hand derivative is limit h tends to 0 plus, this is f of x plus h minus f of x upon h. Okay, now for the left hand derivative, so our function is on the number line, it looks like this. So this is, let's say, 0, 1, and 2. So between 0 and 1, the function is ax plus b. At x is equal to 1, the function value is ax plus b. And between 1 and 2, it's 2x squared minus x. So because we are differentiating it at x is equal to 1, so the left hand derivative for that the function is ax plus b. So the function is ax plus b. For left hand derivative, it's ax plus b, and its x is equal to 1. So this is now limit h tends to 0, negative x is 1. So f of 1 plus h minus f of 1 upon h. Now, so the function for left-hand derivative is ax plus b, and f of 1 plus h will be equal to a into 1 plus h plus b. So let's replace the value here. So, sorry. So this is limit left-hand derivative. Okay, this is limit h tends to 0, negative f of 1 plus h is a into 1 plus h plus b, and f of 1, so let's put the value 1 here, so this will be a plus b upon h. And now let me raise this. Okay, so let's evaluate this. So if I open up the bracket, so this will give me a plus ah plus b minus a minus b upon h. So b and b gets cancelled, a and h gets cancelled. So this is limit h tends to 0, negative ah upon h. So we are left with a. So this is equal to a. Okay, so this is, let's say, equal to a. Okay, now let's find out the right hand derivative. So right hand derivative is equal to, this is equal to limit h tends to 0, positive. Now for the right hand derivative, our function is 2x squared minus x, and f of x plus h. X is 1, so this is f of 1 plus h minus f of 1 upon h. So which is equal to limit h tends to 0, positive, f of 1 plus h. So this is 2. Instead of x, we have to write 1 plus h. It is 1 plus h. So this is 2 into 1 plus h the whole square minus 1 plus h. And function's value at x is equal to 1. That would be 2 minus 1 upon h. Okay, so let's open up the bracket. So this is, okay, so this is 2 plus h square. So this is 2h square. I'm opening up the bracket and at the same time multiplying it with 2. So this is 2h plus 4h minus 1 minus h minus 1 upon h. And finally, we have its limit h tends to 0, positive. This is uh, 2 minus 1 is 1, so this gets cancelled with 1. And finally, we have 2h squared plus 4h minus 1. Let's take h common. So this is 2h plus 4 minus 1 upon h and h gets cancelled, which is equal to limit h tends to 0, positive. And this is 2h plus 3. So if we use a limit now, so this is equal to 2 into 0 plus 3, which is equal to 3. So a is equal to 3. Okay, we have find the value of a, and we have just used the condition of the left hand derivative. So we have used the condition of the function is differentiable at x is equal to 1, where we created the left hand derivative is equal to right hand derivative. Let's use the condition where x is equal to 1. So when x is equal to 1, so that means at x is equal to, so function is continuous at x is equal to 1, so that means at x is equal to 1, so at x is equal to 1, left hand limit is equal to right hand limit. is equal to function's value at 1. Okay, now our function, this is at x is equal to 1, left hand limit will be, so limit x tends to 1 negative, and the function is ax plus b, and the right hand limit is limit x tends to 1 plus, and the function's value is 2x squared minus 1. Now the function value at x is equal to 1. At x is equal to 1, it's so again ax plus b. So this is ax plus b. So at x is equal to 1 and the left hand limit it's equal. So we are going to create the ax plus b. So the function's value at f of 1. So let's put in the value of x here 1, which is a plus b. So a plus b is equal to, let's evaluate. So this and this are equal. So we are going to use the right hand limit with the function's value, and right hand for right hand limits, its limit h tends to 0. Let's say for right hand limit, let's say x is equal to a small value greater than 1. So as x tends to 1, h tends to 0. So this is h tends to 0, and this is 2 into this is 1 plus h the whole square minus x is 1 plus h upon, okay, that's all. And this is now limit h tends to 0. And if I put in the value of h is 0. So this is 2 minus 1. If we evaluate it for the limit, so this will be 2 minus 1, which is equal to a plus b. So a plus b is equal to 1. But we have already got the value of a, which is 3. So that gives me 3 plus b is equal to 1, and b is equal to negative 2, and a is equal to 3. So b is equal to negative 2 and a is equal to 3. That solves our question number 25. And let's move on to section C.